So can we share some of our observations about this graph? What do you guys see? Yeah, okay, so that is actually the answer to the second question. What does this little squiggly line mean? I don't know what it's called either. It's a little squiggly line. It means that there's a break in the numbering, right? So usually the this intersection point between the x-axis and the y-axis at 0, 0, right? So this little thing means there's a break in the numbering. This went from 0 all the way to 3,000 in one jump. So it's just a little heads up, like, hey, we're not starting right at 0 here. Yes. Ooh, yeah. We had it approximately doubled the cost of tuition and fees over 10 years. That's quite a lot, quite an increase to double. Yeah. Anything else? Goes up gradually. This meant break in the graph. Gradual and steady. Yeah, okay. What? Pretty linear. We might not all know what that means yet, but we will. There's only one orange bar. That's a good observation. I wonder if there was something special about the year 2003 that they decided to make it orange. What questions do you have? What tuition was in 2000 or before 2000? Ah, okay. Okay. Yeah. What was tuition like before 2000? Yeah, was it ever free? Yeah, maybe it was higher. Like, yeah, who knows? What was the tuition before 2000? And maybe after 2010. It's 2015 now, right? So this graph is a little old. Right? Yeah, I know. Any other questions that you might want to be interested in asking about? What's it like in other countries? Sure, compare to other countries.
Were there like any huge outliers?
Any outliers?
Private colleges?
Compared to private colleges? Yeah. All right, so that's good. We have lots of questions we can ask about that data. So the good news is that it may be possible to answer some of those questions using math. We can work with the real data collected and presented in the bar graph to find something called a mathematical model, or more simply, a model. A model is a mathematical representation, like an equation or a formula, of a real-world situation. If we can describe the relationship between two or more quantities, if you could describe it in words, we can usually write an equation that relates the two. Okay, so this is an important step in problem solving, being able to convert from a written or verbal description of the relationship to an equation. So I'm going to use math to answer some questions about the cost of tuition and fees using a model. So I'm just going to tell you this formula is a model for the cost of tuition and fees at public four-year institutions, okay? Where X is going to represent the number of years since 2000, and T is going to represent cost. So if I was going to use this formula to find the average cost in 2010, right? I'm looking for T. What do I plug in for X to represent 2010? 10, yeah, because we're measuring years after 2000. X is being measured in years after 2000. So for 2010, X is actually 10 years after 2000. So I'm going to plug a 10 in there for X. So T for tuition is going to be 4 times 10 squared plus 341 times 10 plus 3194. Okay, so I might need a calculator. Yeah, I always love the reaction when I first open this. Okay, so 4 times 10 squared plus 341 times 10 plus 3194, and I get $7,004. So my model, right, my formula predicts $7,004. Okay, how much does the formula underestimate or overestimate the actual cost shown in the graph? So let's go back to the graph, we'll look at 2010. 2010, the actual tuition was $7,020. So we underestimated the actual tuition by $16. Okay, so our prediction, the model's prediction was $16 too low. All right, so now I'm going to use the model, which is the formula, to predict the average cost of tuition in 2014, which is trying to go forwards into the future, and then 1990, so I'm going to go back into the past. So for 2014, what am I going to plug in for X? X equals 14. All right, for 1990, what do I plug in for X? Negative 10 years before 2000. Okay, so I'm going to plug those both into my formula. If you happen to be using a graphing calculator, there's a little shortcut where you can hit second enter and it pulls up exactly the previous thing that you typed. So I'm just going to change my 10s to 14s. And I get $8,752. And then I'm going to change my 14s to negative 10s, right, to predict for 1990. Negative 10, and I need parentheses around that. Okay, so squaring the negative 10, and then here I need a negative 10. All right, so I put negative 10s in, and I get 184. That would be great, yeah. Do you think that that's actually plausible? Do you think that tuition and fees in 1990 was actually $184? No. This is not a good prediction. So models can be incredibly useful, but you also have to use a little bit of common sense, right? A mathematical formula, just because it's a formula doesn't mean it's always right, okay? So this is no, it probably wasn't $184. It was probably more than that in 1990. And this is what we call model breakdown. Okay, when a model gives a nonsensical prediction, we call that model breakdown. And that can happen if you try to extend too far beyond the data that you actually know. So just so we can check, the College Board says that the average yearly cost for tuition, room and board for private four-year schools was almost $41,000 in 2013-14, which was a 14% jump over the past 5 years. 18,000 for four-year school, which was a 20% jump. Okay, so shifting gears a little bit to a new topic. So that was mathematical models. Now we're going to talk a little bit about sets. Okay, a set is just a collection of objects. For example, you could have the set of students in this classroom, the set of large species of cats, or the set of Oscar winners for Best Actress. The objects in a set are called the elements of a set, and you can write a set by listing its elements between curly brackets. And we call that the roster method. So for example, if we let A represent the set of the Three Stooges, then A is the set listed out Larry, Moe, and Curly, and you put them all in curly brackets, separated by commas. So if B represents the set of 7 dwarves, and I wanted to use define it using the roster method, what goes in there?
Can I name all of them?
Yeah, sure.
All right. Happy, Sneezy, Doc, Sleepy, Grumpy, Dopey, and Bashful.
Sneezy, Doc. Sorry, go ahead. Happy, Sneezy, Doc.
Sleepy, Grumpy, Dopey, Bashful. No, I really love Disney like too much. 22 and I love Disney.
1, 2, 3, 4, 5, 6, 7. Yeah, there we go. Listed in curly brackets with commas between them. So that is the set of 7 dwarves. So, however, the sets we're going to be encountering in this class are typically sets of numbers. And there are some ways to write sets of numbers that will help us be more efficient than listing every number that we want to talk about. Okay, so one way is called set builder notation. It's a descriptive way to write a set. Generally speaking, it looks like this. There's a curly bracket, and then there's an X, and then there's a vertical line, and then some other stuff. Okay, so you read this, the set of all X's such that, the vertical line you read such that X meets some conditions. Okay. So for example, if I wrote this statement right here, I would read that as the set of all X's such that X is less than 0. So what set of numbers am I describing when I say that? The set of all X's such that X is less than 0. Negative numbers. Yeah. Yeah, negative real numbers. Yeah, good. Okay, so I'm going to let you play around a little bit with sets and models in the class activity. You've got the answers at the end, and I will help as needed.